Yeah, I'm going to talk about the application of a specific technology, a specific instrument, Doppler LiDAR, for characterizing the physical environment during these greenhouse gas type measurements. And I want to acknowledge all my co-authors. These are all the group that is involved in the Indianapolis study. It's a diverse group from many institutions doing some excellent work. I think most of you know about INFLUX, the Indianapolis Flux experiment, and quite simply it's designed to develop new methodologies or methodologies to characterize the greenhouse gas emissions from large areas, such as urban areas. And there's both a modeling and a measurement effort involved in Indianapolis. Includes 12 in situ tower-based measurements, flash sampling, and a particular important part is aircraft sampling of greenhouse gases done periodically. And then I will talk about the application of LiDAR for these type measurements. Now this slide this cartoon shows the application of how we use aircraft for mass balance estimates of urban emissions. And it's a simple mass balance technique. We fly the airplane upwind and downwind of the area of interest. And with knowledge of the wind, knowledge of the concentration of the greenhouse gases upwind and downwind, and information on the mixing, in particular in the boundary layer, we can calculate the emissions and the fluxes of gases from this urban area. A critical part, a critical aspect of these measurements is knowing the wind profile, and understanding the mixing, and that's where we apply the Doppler LiDAR for these applications. We also apply that because it provides continuous measurements of winds for flight planning, for understanding where to fly and how high to fly. So the information here is useful both in terms of carrying out the experiment and also analyzing the results and the data. This cartoon shows how we do the measurement. Prior to INFLUX, we have done a number of experiments utilizing these techniques, typically looking at oil and gas emissions. We've done this work in Utah, in Colorado, and in Texas, and developed this methodology where we basically take the LiDAR and we go through a sequence of scans that we repeat 3 times per hour, and this includes conical scans, which enable us to measure the wind profile, vertical scans that are done orthogonal to the wind, and that gives us information on both more information on the vertical wind profile and also on the turbulence in the horizontal wind. And finally, we do a sequence of measurements vertically, where we do a staring measurement vertically and look at the variance in the vertical velocity, which is an important parameter to characterize the mixing. And in the lower left, you can't see that very well, but that shows just a sequence of wind profiles where the colors indicate the wind speed and the arrow directions indicate the direction. In the lower right, there are two. This illustrates the vertical velocity variance. You can see as the day progresses, this is a 12-hour period, you get this increase in the variance, which corresponds to the growth of the mixing layer, and it's capped at the top, goes towards 0 at the top. This is the aerosol backscatter from the LiDAR. Again, you see some correspondence to that with the vertical mixing. You see these layers. It's also characterized by residual layers above this mixing layer. So all this information is available. The vertical velocity in particular is quite a useful piece of information, and this just provides a little more detail on that. This is a 10-minute segment here where we see just individual measurements of the vertical motion. You can see the updrafts and the downdrafts. They're connected to the ground. You can see where they sort of die out the top of the mixing layer. And from that, we can compute the velocity variance profile, and we can also compute the skewness, which does have some information, some utility here. And we compress this. This is a 10-minute period, and we compute this profile for 10 minutes, characterize this by the color, and this period here corresponds to this 10-minute period. And you can see, again, the growth of the mixing layer as indicated by this vertical velocity variance, where the variance peaks at about 1/3 of the thickness of the mixing layer. So the work we had done prior to Indianapolis was done with a research instrument that we had characterized at NOAA for many years. But because Indianapolis is a long-term measurement designed to go on for multi-years, this was really not an appropriate instrument. So for this application, we actually purchased a commercial off-the-shelf instrument for Indianapolis. It has the same characteristics in the sense that it's a Doppler LiDAR and provides measurements of the aerosol and the wind velocity, but it also has some differences. In particular, this instrument has much lower pulse energy and much higher pulse rate. And that does have some implications in terms of the data and the characteristics of the data. The average power is about the same, but it's configured differently, and I'll say a little bit about that. So we put this LiDAR to the northeast of Indianapolis at Ivy Tech Community College. It's on the roof. Took a crane to get there. You can see this shows the location. The prevailing wind, particularly in the summer, is from the southwest. You also see the various towers indicated here. We installed this in April 2013. It's been operating ever since, more or less continuously. It was down for about a month for maintenance in July 2013. During this spring, we actually took our other LiDAR to Indianapolis for studies aimed at, one, comparing with these two instruments to look at the comparative performance, and second, to look at, we actually moved this to this part of Indianapolis to look at differences in the mixing layer characteristics spatially, upwind and downwind of the city. Just information on what we get, and these data are computed automatically daily and put on the web. From the small Doppler LiDAR, we get summaries, we get these wind speed and direction plots, we get measurements of the aerosol backscatter, which again is related to somewhat to the concentration of aerosols. We get the vertical velocity variance. These again are 12-hour periods. And then we also we blow this up and get a measurement of the wind speed and direction at high vertical resolution near the surface. And these come in on a daily basis. You can go to the web and see any particular day from Indianapolis. I want to say a little bit about the aircraft comparisons. As I mentioned, the Doppler LiDAR data provide information on both mixing and wind speed that are used in these mass balance calculations. And during the spring this year, we actually did some comparisons where we had the Hurdle, the NOAA LiDAR at the airport in Indianapolis, and the Halo LiDAR at its permanent spot to the northeast. And you can see the flight plan here for the Purdue aircraft, measuring both greenhouse gases and some meteorological parameters. And here's a comparison. And what I show here, this is data from the Hurdle. This is the vertical velocity variance to the southwest of Indianapolis. These are the aircraft profiles over, more or less over, somewhat displaced, but more or less over Hurdle. These are greenhouse gases. This is CO2 and methane profiles. This is measurements of the physical parameters from the aircraft, the water vapor and the potential temperature. And you can see a couple of things here. One, you can see the variability in these 10-minute estimates of vertical velocity variance profiles. That's primarily because it's a sampling error. 10 minutes often is not enough to characterize with high precision the variance in these because of the large eddies, particularly during low wind speeds. So you see quite a bit of variance from 10-minute period to 10-minute period. And that also, of course, would affect the airplane as it does spirals or whatever. You would also be dependent on whether you're sampling within these eddies. So in order to try to characterize the general growth of the mixed layer, we have to come up with a technique to perhaps average or some other way to characterize, to take into account this variability. This is the Halo instrument, which again is to the northeast. The winds were just west of south, so this wasn't truly a trajectory that went across the city. But you can see quite a bit of complexity in the profile here. This is the water vapor. This is the potential temperature. You see this little inversion at about 1,000 meters, and you see the stronger inversion up high. And the halo data seems to indicate that most of the variance in the mixing is below this lower inversion. In other words, we don't see very much scatter above it, and we see the variance top out at about 1 kilometer in this case. We also see somewhat higher, somewhat deeper mixed layer downwind of the city, although these are displaced in time, so that measurement has some uncertainty, or that conclusion has some uncertainty. Another application, and these are just two examples of how we use the LiDAR data for model validation and assimilation. Modeling is a critical part of this effort in trying to develop models to provide these emission estimates. And we use this both in validation. These are comparisons of the LiDAR data. These are errors or differences in the LiDAR measurements versus model measurements of wind speed and direction. The blue is the mean error, and the others are the uncertainties in the RMS error. And then this is actually where the data are actually being used, because the LiDAR provides wind profiles every 10 minutes. These data are very good for assimilation into the models, and we can see how assimilation of the LiDAR data actually reduces the uncertainty. The model is quite receptive to assimilating these LiDAR wind profiles. As I mentioned, we took the two LiDARs and we compared these at Indianapolis, and you can see these are estimates of wind speed and wind direction. This is the vertical velocity. You can see that the estimates of wind speed. I'm sorry, this is wind speed and this is sensitivity. The wind speed estimates are quite good, and you can see the difference in sensitivity between these two instruments. This is about a factor of 10 lower in sensitivity, the HALO LiDAR relative to the NOAA LiDAR, and that does show up in some of the profiles, and I'll just say a little bit about that. You can see this here. These are measurements where we compared these two. This is the HALO instrument. This is the HRLO instrument. You can see you get much better vertical penetration with the HRLO instrument, up to about 2 kilometers in this case, where this tends to peak out at about 1,500 meters. You also see this in the aerosol field. Again, not much greater, but greater penetration with HRLO. So the question for us becomes: are we seeing the full boundary layer? Can we see this continuously with HALO? And we've been trying to come up with a metric to look at that. And what we're looking at now is we look at the maximum range using two different parameters. One is the signal noise ratio, and one is the vertical velocity variance. And we compare the horizontal max range with the vertical max range. And we reason that the horizontal range we should be seen farther horizontal than we are vertically. If we run out a signal vertically at the same distance we run out horizontally, we probably are not seeing the top of the mixed layer, which should be characterized by a gradient. And so what that means is we should see most of these plots below this line, and in fact we do for this period. And so again, it's a relatively crude test, but to some degree, this tells us that for a large part of the time, we appear to be seen to the top of the mixing layer. Having said that, we are also in the process of upgrading this instrument, and so we will, next month, we're going to ship it back to the manufacturer and try to make some modifications to improve sensitivity. So I'm just going to conclude here and just point out that we have operated for a year and a half. This instrument will continue to operate. It'll be upgraded, and the data, we're still looking at ways to an automated method for measuring the depth of the mixed layer and providing that on a regular basis. Thank you.
All right, we have a little bit of time for questions. I see one down the back there.
So on your HALO LiDAR, the backscatter that you get is a concentration of aerosols, so those aerosols can be any.
That's right. I mean, it's really, there's no differentiation. The instrument tends to be sensitive to aerosols of a certain size, but composition, it's really a matter of refractive index and scattering characteristics of the aerosols. That's right.